Alright, in our last video in Chapter 8, we're going to look at the strength and length of covalent bonds. Earlier in the chapter, we talked about the strength of ionic bonds. Ionic bonds, remember, were governed by something called lattice energy. Lattice energy was governed by an equation. Well, in covalent bonds, there is a table of enthalpies of these bonds, or energies of these bonds, and they're given us a fancy name. They're called bond enthalpies. And so the strength of a bond, like between CH right here in the molecule of methane, is averaged, because this bond might be a tiny bit different than this one, but they just take all four and average them out, and they call it the average bond enthalpies for a CH bond. You can find these on the digital book, page number 365, or the physical book 326 in table 8.4. And so you can see that a CH bond has an average bond enthalpy of 413 kilojoules per mole. A carbon-carbon bond is 348. And you kind of look around at a lot of these different values, and you can see that an oxygen-oxygen bond is 146. But something interesting to note is when you get to a double bond. So a double bond carbon, a single bond carbon is 348, a double bond is 614, a triple bond is 839. So you can notice it's not quite double or triple, it increases a significant amount though. And you can see a nitrogen-nitrogen double versus a nitrogen-nitrogen triple, even more than doubles in that case. From a nitrogen-nitrogen here, nitrogen, you can see that they change. So the more bonds you have, the stronger that they are. The second thing is the length of covalent bonds. And covalent bond length is very related to its strength. So the length of bonds can be found on a table in page 368 on the digital book, or table 8.5. And you can see right here that the length of a carbon-carbon single bond is 1.54 angstrom, whereas a double bond is 1.3 and a triple bond is 1.2. So you can see that as they get stronger, the length gets shorter. And it holds true over here in nitrogen bonds too. A single, a double, a triple, you can see that the length gets shorter as you have more and more bonds. So more bonds, the length gets shorter as it gets stronger. So what can we do with these? Well, using these strength or bond enthalpies right here on the page before, this page right here, we can calculate, or use them to calculate, an approximation of an enthalpy of reaction. So I'm going to move this paper right here, and I'm going to put this using bond enthalpies page up with one example problem, and we can use them to calculate the enthalpy of a reaction. The way we do that is through this equation. The enthalpy of reaction is approximately equal to the summation of the average bond enthalpies that are broken. This is the summation sign, by the way. It means add them all together, minus, or the difference between, the summation of the bonds that are formed. So bonds broken minus bonds formed. So that's usually the reactants minus the products. We're going to do one sample exercise on page 367. It's sample exercise 8.12, and I'm just going to turn to that page right here, and I'm going to zoom in on it so you can see the example. So it says, using data table 8.4, estimate the delta H for the combustion reaction. And I'm going to draw this combustion reaction while you write it down. There's two of the molecule ethane, and this is the Lewis dot structure for it, plus 7 of these O's. And I'm going to draw the Lewis dot structure for it right away. In case you don't know, the Lewis dot structure for oxygen has a double bond in it like that. And then that arrow is going to go over here, and it's going to make carbon dioxide, 4 of them, so 4. And I'm going to draw it this way so it fits on the paper. CO2s, plus I have 6 of these waters, so 6, and I'm going to draw them this way again so they fit, 6 Ch8.8s like that. Unshared pairs of electrons on there. I'll put parentheses around there so I don't get them too confused. And there's my reaction that I want to find the enthalpy of reaction for. So delta H then would be equal to the bonds that are broken, which would be these guys, because those are busted, minus the bonds that are formed, which are these guys right here. So let's go back a page right here to the bond enthalpy table, and let's see if we can find each one, and we'll add them all up. So first of all, bonds broken. We have a carbon-carbon bond right here in the middle. 348. There's two of them because there's two molecules right here. So 2 times 348 plus 1, 2, 3, 4, 5, 6. 6 carbon-hydrogen bonds right there. There's 2 of the molecules, so 2 times 6 is 12 of these CH bonds, so 12 times 4, 13. So that takes care of this molecule with the bonds that are broken. Plus, now we have 7 of these oxygen-oxygen bonds on this reactant side. So 7 times an OO double bond is right down here, 495. So that's my bonds broken, minus my bonds that are formed over here. So my bonds that are formed are a carbon-oxygen double bond. And if I look right down here, here's a carbon-oxygen double bond, 799. Too bad they just didn't round that to 8 for us. So 2 in here and 4 of those molecules, so that's 8 times the 799er. Plus, now I've got an OH bond right here, 2 inside of this molecule. So here's the OH bond right here, 463. So 2 in here, there's 6 of those molecules, so that'd be 12 times the 463. Now, 2 times this, plus 12 times this, plus 7 times this, minus, and then do all this at once, 8 times this, and 12 times this. Once you do that all on your calculator, then you should end up with some mathematics that looks like this. This side, it looks like, adds all up to 9117 kilojoules. This side, it looks like it adds up to 11948 kilojoules. And so we end up with a negative 2,831. This is all measured in kilojoules, and this would be equal to our delta H of the reaction, and we'd be pretty close. So, bond length, bond strength, related in that short bond is a strong bond, or vice versa. A strong bond is a short bond. And we can use the bond enthalpies to help us calculate the enthalpy of a reaction.